Sorry to cut that last video a little bit short, but I was starting to say there's a lot of different ways you could have set this up to test for independence. You could have done probability snowmobile owner equals probability snowmobile owner given environmental club member. You could have used one of these formulas, the probability of snowmobile owner and environmental club equals the probability of snowmobile owner times the probability of environmental club. Any one of those three ways would have worked. You're not going to get the same decimals. You're not going to get 20% and 5%, but you're going to get two decimals that are not equal or two probabilities that are not equal. Just keep in mind all probabilities are between 0 and 1. So moving on to the next section of the lesson, page 4 is just practicing this learning objective about independence. So what I'd like for you to do is pause the video and then work through page 4 and then come on back. All right, going through page 4 here, they want to know, are the events female and longer ring finger independent? There's three ways to test for this. So you may have different values than I do. I just set it up probability of longer ring finger equals probability of longer ring finger given female. Probability that the ring finger is longer, let me see, for me, that's true, is 52%. But given that you're a female, the probability that your ring finger is longer is only 39%. And I'd be curious in class today, just take a look for males. It's more typical that your ring finger is longer. And for females, it's a little more typical that they're about the same. It'll be split. So given that you're female, this is only out of 212. 82 had a longer ring finger, which is only 39%. So these events are not independent. Make sure you answer the question. No, the events F and LRF are not independent. And you could just say because probability of longer ring finger does not equal probability of longer ring finger given female. But the understanding behind it is knowing this event occurred that someone was female, that changed the probability that their ring finger was longer. For question 3 on the bottom, they want to know, are the events female and right-handed independent? So you had to figure out the totals for the two-way table. So probability that someone was female in this class was 21 divided by 28. Probability of female given they're right-handed, there's 24 right-handers, 18 were female. This is both 75%. So given that somebody was right-handed, it did not change the probability that they were female. That's what makes these events independent. We have no additional information. They're not more or less likely to be female. All right, so moving along. Page 5. This gets into this learning objective of using the multiplication rule for independent events to calculate probabilities. And the multiplication rule is something that has a formula attached to it, but to be honest, I don't think we ever officially use the formula. It's just understanding what to do when we have independent events to calculate this. So all of you are probably too young to know about this, but in 1986, the spaceship or space shuttle, the Challenger, exploded on takeoff and killed all the crew members. So they went through and analyzed why this happened. And they determined that they have these O-ring joints, that there's 6 of them, and if some of them fail, it affects the launch, the safety of the launch. So essentially, they found the probability that one of these joints would function properly is 0.977. And they had all 6 had to function properly for the shuttle to launch safely. Now, we have to make this assumption that they succeed or fail independently, meaning if one of the rings succeeds, it doesn't affect the probability that the other one succeeds. Find the probability the shuttle would launch safely under similar conditions. So what we're going to do here is use notation, as we've been doing. Probability all 6 work. Or probability launch safely, just something that communicates what you're finding the probability of. So for us, we know that the probability that one of these works is 0.977. But really what I'm finding is the probability the first one works, and the second, and the third, and the fourth, and the fifth, and the 6th. And we know if events are independent, we can multiply the probability of A and B The probability of A times the probability of B gives me the probability of A and B. So I can just multiply. The probability that each one of these works is 0.977 for all 6 of these. So I can multiply 0.977 by itself 6 times or raise it to the 6th power. When we do that, we get 87%. When you think about this in terms of the real world, this is kind of messed up. Like, there's an 87% chance that the space shuttle would launch properly. Well, I would not be willing to take that risk, 13% chance that it doesn't. So just a nice application of statistics as far as how it's used and how it can, in this case, save lives or avoid disasters. The second skill we're going to use this multiplication rule for is finding the probability of at least 1. This is incredibly important here. At least 1 and none are opposites. What the heck does that mean? If I'm taking at least 1 AP class, the opposite of that would be I'm not taking any, because at least 1 means 1 or more. So the opposite of at least 1 is none. All right, a few decades ago, there was a big issue with AIDS and HIV. That's since diminished with the kind of progression of medicine. But you had a lot of people who came to clinics to be tested for HIV, the virus that causes AIDS, and they don't come back to get their results. So they wanted to change that, so they came up with rapid tests. And they increased the percent of clients who learned their test results from almost 70% to almost 100%. The trade-off was the test isn't quite as accurate. So now we have a probability that one of these rapid tests gives a false positive 0.004 of the time. So a clinic test 200 randomly selected people who are free of HIV antibodies. What is the chance at least one of them gets a false positive? So really, if I think about this in terms of numbers, I have 0, 1, 2, 3, 4, 199, 200. At least 1 means I need the probability of 1 or 2 or 3 or 4. This calculation would be completely overwhelming to do. So knowing that at least 1 and none are opposites, that's what we're going to do. We're going to do probability at least 1 false positive equals 1 minus the probability of no false positives. The way that we do this, we do 1 minus the probability that they have a false positive is 0.004. So the probability that they don't have a false positive is the complement, 0.996. But I need 200 people to have no false positive. Assuming each person's results are independent of the next, I can just multiply because they're independent events. And this calculation is going to give me 55%. So that means at least one of the 200 people is going to have a false positive result 55% of the time. So there's that trade-off there. So it's the same concept, this idea of the multiplication rule for independent events, but I'm using it slightly differently. At least 1, I'm going to do 1 minus the probability of none because they're opposites. They're complements in that sense. All right, so what I'd like for you to do, pause the video and work through these 2 questions on the bottom, applying this multiplication rule. So what you'll notice on the first one, they tell you, assume the missions are independent, find the probability the bomber returns safely from 20 missions. 5% is the chance that it's lost, so 95% the complement is the probability it returns safe for 20 missions. Each one's independent, so I can multiply the probabilities. So 0.95 to the 20th, 0.358, or about a 36% chance that it returns safely, which is not very high. All right, this question about pregnancy, at least one woman will receive a positive result. So you have to go back to this concept, at least 1 and none are opposites. So it's going to be 1 minus the probability of no positives. So 5% are positive, 95% aren't. Each result is independent of the next, so that's why I can multiply these probabilities. So 1 minus the 0.95 to the 100th is 0.994. So it's extremely likely at least one woman's going to have a positive result. All right, that's the end of part 2.